Okay, welcome back. So now we are going to talk about how equilibrium, this concept that we talked about in chapters 15, 16, and 17, these ideas of equilibrium, how those relate to spontaneity. So really, this is the point that we can connect our entire semester. Because remember that equilibrium was connected to kinetics in that when a system is at equilibrium, it is when the rate of the forward reaction equals the rate of the reverse reaction. And now we see that equilibrium plays a role in spontaneity. And so this is kind of the thread that connects all of the topics that we have been talking about all semester. Okay, so let's remember what's going on with Q and K. So remember that if we have our generic reaction, A plus B is in equilibrium with C, our reaction quotient, it has the expression of the concentration of C divided by the concentration of A times the concentration of B. And remember that our reaction quotient has the same form as our equilibrium constant. It's just that the concentrations that go into it are not their initial concentrations. They're not equilibrium concentrations. Whereas in our expression for our equilibrium constant, the concentrations have to be equilibrium concentrations. And so if we remember these relationships, if Q is less than K, then the reaction proceeds spontaneously to the right towards the products. If Q is greater than the K, the reaction proceeds spontaneously in the reverse reaction towards the reactants. And if Q equals K, then the reaction is at equilibrium, and both the forward reaction and the reverse reaction are happening at the same rate. So, if Q divided by K is less than 0, this means that K is bigger than Q, then delta G is negative and the reaction is spontaneous. We're going to call it good, close enough, as written. If Q over K is bigger than 0, that means that Q is bigger than K, then delta G is positive, and the reaction is spontaneous in the reverse direction. If Q is equal to K, then delta G equals 0, and the reaction is neither spontaneous nor is it not spontaneous. Delta G can also be given by this expression that delta G equals minus RT times the natural log of Q divided by K. If Q and K are very different, then the reaction releases or absorbs lots of free energy. There's a lot of reaction that has to happen in order for Q to equal K and the reaction comes to equilibrium. If Q and K are close, then there's very little free energy that is released during the reaction. So, if we use things in the standard state, we are given that delta G equals minus RT ln K. And this is our standard condition, delta G. If we don't have standard conditions, then we're given this delta G standard plus RT, L, and Q gives us this non-standard condition delta G. This is the delta G that is very prevalent in biology and biochemistry, because it turns out that our bodies are not at equilibrium. And so when we think about systems in biochemical systems and what is driving those and the delta G involved, we have to think about them in non-equilibrium conditions, because the enzymes, the proteins, the systems involved in our body is working to keep us away from equilibrium. But whenever we think about pure chemistry and pure reactions, most of our reactions are at equilibrium. And so for the most part, for pure chemistry sorts of studies, we are looking at this delta G standard. Okay, so let's do an example. We have the oxidation of sulfur dioxide is too slow at 298 Kelvin to be useful in the manufacture of sulfuric acid. So the reaction is normally run at 973 Kelvin. And it gives us the values of delta G at each temperature. It says, using this information, determine the equilibrium constant at both temperatures. So to do this, we're going to do delta G equals minus RT ln K. And the first thing I'm going to do is I'm going to rearrange this equation so that I get rid of the natural log and can plug things in a form that has K isolated. So I divide both sides by RT. To get to rid of the natural log, I need to raise both things to the E. And so I get E raised to the delta G over RT equals K. Now the next thing that I'm going to do is I'm going to convert these delta G's to joules. And so at 298, I get negative 1.416 times 10 to the 5th joules per mole. And at 973, I get negative 1.212 times 10 to the 4th joules per mole. Okay, so now I'm going to plug things in. And so let's first do 298 Kelvin. And so I get E raised to the negative 1.416 times 10 to the 5th joules per mole, divided by R is 8.314 joules per Kelvin times mole, and my temperature is 298 Kelvin, is equal to K. So this gives me E raised to the 57.15 is equal to K, and so K is equal to 6.62 times 10 to the 24th. Okay, and so now we're going to do the same thing, only with the values for 973 Kelvin. I get E raised to the negative 1.212 times 10 to the 4th joules per mole, divided by 8.314 joules per Kelvin times mole times 973 Kelvin is equal to K. And so I get K is equal to E equals E raised to the 1.498 And so K is equal to 4.47. Okay. So there's those examples. And we're going to, in the next video, we're going to start talking through these ideas in broad context and how we combine finding this equilibrium constant to getting out enthalpy and entropy values in the lab and kind of putting all of this together.